Hi all, today's topic of discussion is hyperconjugation, which is the fourth electron displacement effect. Here, the delocalization of electrons by the overlap of sigma bond orbital with a pi bond orbital is called hyperconjugation. In the last class, we have seen resonance effect. In that, we have seen that in this resonance structures are obtained by the delocalization of pi bonds. Here, there is a difference. A sigma bond is in conjugation with a pi bond. And in the hyperconjugative structures, you cannot see one proper bond. At some places, the proper bond will be missing. That's why it is otherwise known as no bond resonance. Hyperconjugation is otherwise known as no bond resonance. I'll explain by taking an example in the coming slide. Okay. Since this delocalization of electrons bring about a lowering in energy, hyperconjugation is also a stabilizing interaction, just like mesomeric effect. For illustration, I have taken the example of propene. In propene, there are 3 hydrogen atoms which are connected to the unsaturated carbon atom. This one, I have just for the sake of more clear understanding, I have numbered as H1, H2 and H3. Here, let's see what happens to H1. Here, the shift of bond pairs takes place like this. So that here was the position of H1. Now H1 gets the positive charge because its electron is transferred to this C double bond C, to this carbon-carbon single bond. Now it has become double bond, and as a result this bond has shifted and converted as a negative charge. Okay, this is the first hyperconjugative structure obtained for propene. And like the same, we can write it for H2 also. The same process happens. And the second hyperconjugative structure will be like this. H2 will get a positive charge and here will be a double bond and here will be a negative charge. Like the same, H3 will be having a positive charge and this will be a double bond and CH2 will have a negative charge, which means that in the case of propene, it has 3 hyperconjugative structures possible. Hope it is clear. Now let's see the applications. Just like in the case of propene, we can write that for different alkenes and we can compare the stabilities of these alkenes. Here we are taking the example of 1-butene and 2-butene. And we have to say on the basis of hyperconjugation, we can say that which is more stable. And for that you have to bear in mind some points. The greater the number of hydrogens attached to the carbon at the alpha position of the double bond, the greater will be the number of hyperconjugative structures. Okay, the greater is the number of alpha hydrogens attached to the double bond, the greater will be the number of hyperconjugative structures and that will be more stable. Okay, here in the case of 1-butene, there are 2 hydrogens attached to carbon-carbon double bond and therefore it has got 2 hyperconjugative structures. Okay, but in the case of 2-butene, there are 6 hydrogens attached to carbon-carbon double bond, and as a result, there will be 6 hyperconjugative structures. And because 6 is a larger number when compared to 2-butene will be more stable than 1-butene, and the illustration comes in the next slide. See, in the case of 1-butene, this is 1-butene, 1, 2, 3, 4. Okay. Okay, here there was a mistake. It's not there. CH2 double bond. This is 1-butene. 1, 2, 3, 4, and this carbon is not there. Please excuse me for that mistake. And this is CH3. Okay. CH2 double bond CH, CH2, CH3 is 1-butene. Here, anyway, we don't need that part, but still, that was a mistake. Please correct it. H1 and H2. Here, two hydrogens are there in the alpha position, which means which is just next to the carbon-carbon double bond. And I'll write you one example. This is the H2 and this is H1. H1 gets positive charge now and this bond becomes double bond. And as a result, this double bond is shifting towards this carbon atom. Okay, so the first structure obtained is CH3 single bond, CH double bond, CH single bond, CH2 minus with the H1 plus. And in the second example, there will be CH3 and here it will be H1 itself and here it will be H2 plus, and this will be a double bond and here you will have a negative charge, which means that we have obtained two hyperconjugative structures for one butene. Hope it is clear. Now let's check the case of 2-butene. In the case of 2-butene, H1, H2, H3, and you can see here 3 hydrogens are there and here also there are 3 hydrogens, and these hydrogens are next to this carbon-carbon double bond. Okay, so we can write it as H4, H5 and H6, and I'll show you only one resonance structures and the rest will just go on like that. Okay, so in the case of H1, this comes down and this goes here and you will get H2 CH3. Here is H1 plus, and this single bond, carbon-carbon single bond has become double bond CH, and this double bond has become a single bond CH minus, and here is CH4, H5 and H6. Like this, we can write 3 from this side, and in the next 3 examples, the bond shifting will be like this, just the opposite, like H4, it will come here and it will go like this. Okay, so we will get 6 hyperconjugative structures, and with this evidence we can say that 2-butene is more stable than 1-butene, because in 2-butene there are 6 hyperconjugative structures and in the case of 1-butene there are only 2 hyperconjugative structures. And the second example is, or second application is, the relative stabilities of alkyl carbocations. You know that carbocations are species in which the carbon is having a positive charge, and methyl, ethyl, isopropyl and tertiary butyl are the normal alkyl carbocations we are studying. And in the case of methyl carbocation, there is hyperconjugative effect is not taking into play because there is no other next to the positive charge there is no other carbon atom, so hyperconjugative effect is not applicable in the case of methyl carbocation. And we have to bear in mind that instead of this carbon-carbon double bond, now we are explaining hyperconjugation by taking the carbon carrying positive charge as the reference. In the previous examples, in the case of propene and butenes, we have taken the center as carbon-carbon double bond and we have checked the number of hydrogens which is attached to the alpha position. Now we have to see here in the case of carbocations, we have to see the number of hydrogens attached to the carbons next to it. Okay, at the alpha position we can say. And here in the case of ethyl, this is ethyl carbocation, we can say there are 3 hydrogens present which are able to exhibit hyperconjugative effect. And I'll write 1. So this is H1 plus and CH double bond CH2 is becoming, because this positive charge is lost because it received, this carbon received an electron from the neighboring carbon atom. Actually that neighboring carbon atom donated the electron by taking it from this hydrogen. That's why this hydrogen received a positive charge. Okay, or it lost its electron. Okay, hope it is clear. And here as a result we can write like this, there are 3 resonance structures are possible. And next we can see the ethyl we have completed, and now see the isopropyl carbocation. Isopropyl carbocation is CH3 CH plus CH3. This is the isopropyl carbocation. And in the case of isopropyl carbocation, we can see that there are 3 hydrogens here, and like the same there are another 3 hydrogens here. So altogether we are getting 6 hydrogens which are at alpha position to the carbon carrying positive charge, and therefore you will get 6 hyperconjugative structures like this. Okay, I haven't numbered because like this you will be getting 6 hyperconjugative structures. And in the case of tertiary butyl carbocation, this is the structure of tertiary butyl carbocation. Here you can see that 3 plus 3 plus 3. there are total 9 carbon atoms which are at alpha positions with respect to the carbon carrying positive charge. Okay, there are 3 methyl groups and therefore there are 9 hydrogen atoms. Therefore, this tertiary butyl carbocation exhibits 9 hyperconjugative structures, and therefore it is the most stable one. Then next, the following is the isopropyl with 6 hyperconjugative structures, and which is followed by ethyl carbocation, which is having only 3 hyperconjugative structures, and the last one is the methyl carbocation because it doesn't have any hyperconjugative structures to exhibit. Okay, so this is the order of stability of alkyl carbocations. And the same with analogy, we can extend it to the relative stabilities of free radicals also. Free radicals are species in which carbon carrying a single electron, odd unpaired electron, R dot. Here also we can say that normal alkyl free radicals are methyl, ethyl, isopropyl and tertiary butyl. And this is the ethyl, this is methyl free radical and it is not exhibiting hyperconjugation. So that is cut off. And now we can see this is the ethyl free radical which is having 3 carbon atoms, which is having 3 hydrogen atoms at the alpha position of carbon carrying this odd electron. And now we can see that just like in the case of carbocations, here in the case of free radicals, homolysis takes place. So this bond breaks like this and therefore a bond is formed like this to give you H1 here. It's not plus, it is H1 dot. Okay, and here this bond has become a double bond. So in the case of ethyl free radical, we have obtained, I have shown only one structures and there are 2 other structures are possible. Okay, so altogether it forms 3 structures. In the case of isopropyl free radical, now I can skip because I hope you have understood from the previous example itself. There are 3 plus 3, 6 hydrogen atoms which are at alpha position to the carbon carrying this free radical part. Okay, and you'll be obtaining 6 hyperconjugative structures. And this is the structure of tertiary butyl free radical. This is the tertiary butyl free radical. Okay, and there are 3 plus 3 plus 3, 9 structures, 9 hydrogen atoms, and as a result you will be obtaining 9 hyperconjugative structures. Okay, this is just the copy of the stabilities of alkyl carbocation so that you can memorize it easily. And the fourth and last application is the Bakernathan experiment. Baker and Nathan conducted an experiment. They have taken benzyl bromide, and this is benzyl bromide by omitting this alkyl group, and they have fixed different alkyl groups at the para position such as methyl, ethyl, isopropyl, tertiary butyl, etc. And they studied the reaction mechanism and the rate of the reaction. Okay. Their aim was to see which substrate gives the highest yield of the product or easiest way how it is obtained. Okay, and for that they have at this para position they have fixed the different alkyl groups and tested for the reactivity. And the expected order of reactivity, we know that this alkyl groups are having plus I effect, and we have seen that in the first video of the electron displacement effects. Because of this plus I effect, these alkyl groups are shifting its electron pairs, electron density towards this benzene ring, so that the electron density is increased here, and we are expecting that as the bulkiness, as the group is becoming bigger and bigger, the plus I effect also increases, and therefore the order of reactivity will be having this order. Because methyl, if your methyl group is attached, the reactivity will be least, and if tertiary butyl group is attached, the reactivity will be the highest. Okay, this was the expected order, but to the surprise of the researchers, the actual order came out to be just the opposite of the expected order. It showed that methyl group is having highest reactivity and tertiary butyl group is having the lowest reactivity. This was a problem over there because this was not explained by taking the inductive effect and resonance effect alone. So hyperconjugative effect came for their rescue, and this one explained why this methyl group is having highest reactivity. Here is the explanation. In the case of this methyl group, there are, see, this is the carbon which is directly attached to the benzene ring, and there are 3 hydrogen atoms present. Okay, so here, since this is resonance stabilized, for H1 also it will give 3 other structures, but I have not mentioned that one to decrease the complexity. Okay, I'm just telling you that there are 3 hydrogen atoms to give the corresponding hyperconjugative structures. Okay, there are 3 hydrogen atoms to give the corresponding hyperconjugative structures. Okay, now let's see. In the case of ethyl group, when we are attaching the ethyl group, actually the carbon, this is the double bond we are considering. Okay, this is the double bond we are considering. Here the number of hydrogens attached to this carbon atom, the alpha position, the carbon at the alpha carbon has reduced, because instead of 1 hydrogen, a methyl group has been attached, and here there is no hydrogen present, and the only possible hydrogen atoms to undergo this hyperconjugation is reduced to 2. In the case of methyl group, there were 3 hydrogen atoms to undergo hyperconjugative effect, and in the case of ethyl carbocations, there are only 2 hydrogen atoms which can undergo hyperconjugation. And now we can see that in the case of isopropyl group, in the case of isopropyl, the H2 is replaced by a methyl group, another methyl group, and as a result, there is only 1 hydrogen atom which is capable of undergoing hyperconjugation. Okay, so again decreased. And now see the last one, tertiary butyl. Tertiary butyl means H1 is also replaced by methyl group. Which means that the carbon at all the 3 hydrogen atoms have been replaced by this methyl group. Therefore, there is no hydrogen atom present which is capable of undergoing this hyperconjugation. So, as a result, we have seen that as the number of hyperconjugative structures increases, the stability increases. Okay, therefore this substantiates the actual experimental order, because in the case of methyl group there are 3 hyperconjugative structures. Ethyl there is only 2, in isopropyl there is only 1, and in tertiary butyl there are no hyperconjugative structures possible. Therefore, this order is justified. Okay. So I have explained the definition and 4 applications of hyperconjugative effect. Thanks for listening to me.